put this live on YouTube. It should be there in just a moment. We have the entire A-term speakers are filled out. And we're starting to fill out B-term. That should come soon. And today, Maya Shahabi is going to introduce our speaker. She's hosting the speaker, so please go ahead.
Okay, all right.
Thank you everyone for joining this seminar session. It's my pleasure to introduce Professor Mao to you. Professor Mao had his bachelor's at Tsinghua University in Beijing, China, and then he moved to San Diego and studied his master's and PhD in UC San Diego. Then looking for shorter summers, he moved to Mass, and he was an assistant professor in UMass Lowell for more than 6 years. And he has recently joined WPI Mechanical Engineering Department as an associated professor. His research interests include dynamic and vibration, intelligent system, signal processing and machine learning, condition-based monitoring of manufacturing and infrastructures, risk analysis, statistical modeling, and prognosis. His work is highly recognized in different conferences. He has also received more than $3 million for funding of his research from NSF, Department of Defense, Department of Energy, Department of Transportation, and also industry sponsors. He has also received multiple awards and scholarship, and most importantly, he is devoted to teaching, and he has been awarded the Teaching Excellence Award at UMass Lowell. His talk today is on digital twinning, a digital twin of dynamic characteristics and prognosis via deep learning and advanced sensing. So it is our pleasure to have you as our speaker, Professor Mao, and I'm going to stop sharing, and it's all yours.
Okay, thank you. Let me share my screen. I think I need to make sure. Which screen do I need to swap? Is the slides all set? Do you see my
the other way
presentation mode?
The slides and the notes.
Oh, okay. So I need to swap again.
There we go.
Now it's better. Okay. All right. Yeah. So I'm very happy to be here virtually today to deliver the presentation. As Maya just introduced, so I've been new to WPI, so probably I've been to WPI for only a few weeks, and so that being said, all of the work I would say none of the work has were done here. But the topic, as the introduction shows you, is about digital twin for different dynamic systems and data processing, right? So the first thing is I want to run it on a high level because I figured out, like, most of you guys are material and manufacturing students, not in this with the same background as I have. So. But anyway, the big picture for my presentation today is I'm going to introduce you how I process the data acquired from condition-based monitoring for different machines or different platforms, especially via artificial intelligence, right? And the second part is how we leverage the advanced sensing, especially computer vision or camera-based sensing, to do system identification. So again, so everything is on the big umbrella of digital twin, but actually more specifically, we are talking about system identification, damage detection, diagnosis and prognosis, that sort of things. So particularly people call this structural health monitoring or modal analysis. There are different names in different subsets of the digital twin, big idea of digital twin. All right, so you might have heard of this term before, but actually it's just as it verbally says, right? It's a digital twin of any physical system. So Probably you will be familiar with finite element analysis or structural testing or fatigue testing, sort of those, right? But you will very quickly realize if there is a damage or if there's any material change to a structure, and your finite element model will no longer predicting the behavior of the structure or of the system, right? So in that case, we have to do something called model updating. So if you update your model in real time, and you can call it a digital twin, right? Why is digital? Because it's a virtual model or a CAD model, right? And it's a twin because it's identical. Well, we try to make it as identical as we can, right? So the far goal is we want to gain state awareness. We want to predict the load, right? We want to identify if there's a damage, where's the damage, what type of a damage, how big the damage is. And the very last question is probably, given this much of a damage, this type of a damage, this location of the damage, how long can your system last, right? Without any further, without any fixed or maintenance. So, well, apparently there are challenges, right? And there are a lot of challenges for this very nice but ambitious idea, right? The first one I'm listing here is getting a high fidelity model for the system operation and deterioration is really hard. Sometimes it's even not possible, right? Because the system, there are so many nonlinearities, unstationarities, so many things that we're not so clear in terms of the physics, right? And there are a lot of operational and environmental variations. So in that case, you can't, we call it noise or some uncertainty sometimes, right? So, but nevertheless, this digital twin idea can apply for many different ideas, right? It can be applied to a machine or to an airplane or to a bridge, to many different things. So let's just take a look at a very simple example here. So these figures are, I downloaded them from Google, and just conceptually showing you the gradual accumulation or progress of a damage, right? So now I mentioned the word damage. What is a damage, right? If you buy a new car from the dealership, I guarantee you the very first day, you will see a lot of flaws or defects on the car, right? It just matters like how detailed you're looking at your new car, right? So what is the damage? The damage defined in this context, in the context of structural health monitoring or damage detection, is the big enough defects that is affecting your performance, right? If you have like a bearing here, but the color isn't really what you wanted or isn't really what is designed, right? And that is not called a damage. That's just something like not perfect, but it's not a damage. And on the lower part of my slide, you see like two curves, right? On the lower left is a time series. If you have a bearing running or rotating, and if you see like a gradual changes of the damages, and you will hear the rattle, you will hear the noise, right? If you drive a car, the car is
like this.
Is that part of a damage? I'm sorry. So you see like the vibration data, acceleration, is getting bigger and bigger, right? Or if you're driving a car, you feel your car is shaking bigger and bigger. So at some time, you want to say, stop, turn it off, or stop the car, right? Because it's too much vibration. And at the same time, if you can just extract some features to measure the vibration, the oscillation up and down, right? Sometimes we use like a standard deviation or variance of the signal or energy of the signal, right? So then you can transfer that into a index. You call that index. If the index goes too poor or goes too big, you call it a damage, right? So in that case, you have to have a threshold. That means when you are defining a damage, you have to have a threshold to make a decision how big the flaw is. It has to be big enough to affect your performance, and how big the damage is that you are going to shut down your machine, right? So in this sense, it's a little bit subjective, right? Right. So it's, let's say, like for this degrading feature on the bottom right. So you can just draw a threshold here, and then that will give you a much shorter lifetime, right? If you just give them more tolerance, it will give you much longer lifespan. It's the same thing as you just do a car maintenance, right? When you do an oil change, it's all depending on how tolerating you are, right? You can just change your oil every month. So then the question is, we have the raw data. We know there is something like a going poorer and poorer, right? And how are we going to model it? Or how are we going to learn from the data and when to stop the machine or when to do the maintenance, right? So there is something like a very popular called deep learning, right? So that means like we assign some artificial neural network to the data, and then we train the model. We train a neural network to get those coefficients from the data. And then once we finish training the data, we can use, finish training the model, and we can use the model to do prediction and to do classification or other type of stuff. So if you are not familiar with this idea, just think about a curve fitting, right? Like curve fitting of these two curves, the green and the blue curve, right? It's all about curve fitting, but it's more sophisticated. So once you have that model, let me just skip the math here. Well, so particular, this is called long short-term memory. So this is the machine learning, this particular machine learning model, and the optimization. Well, the curve fitting. So you know, like when you are doing machine to do the curve fitting, you have something called like a least square fit, right? Something like that. So this is the similar thing. So you have to have a optimization algorithm to train a model, and once it's all trained, so you will have a data-driven model, and that data-driven model can tell you something, right? So let me just show you an example before you get lost in the math. So we have downloaded some like an open challenge problem, the data from IEEE, prognosis and health management organization. So so there's a pretty big amount of a data set available, and then we train the models, and as I said, the model is called LSTM. So it's a sort of a recurrent neural network, and we apply a convolution. We add convolution layers to the recurrent neural network. So that is the new model that we applied, and here's the result. So you see from this figure, right? That is pretty similar to what we have seen before, right? A few slides before. You have a fundamental oscillation, and from time to time you have some spikes. But as time goes by, it's just gradually increasing its magnitude, right? And you know there's something that goes wrong after, let's say, 7.5 hours, right? So when we fit the data into the data-driven model, or the recurrent convolutional neural network, and this is the result that we have, right? So the x-axis is the time, and the y-axis is the remaining useful life. So apparently, like if you keep going, the remaining useful life is going to be 0, right? And the red curve is the prediction from this DRCNN model. And we compare our model with a conventional model people using. We got like a pretty big improvement over 30%, right? So anyway, the idea, the take-home message here is if you have data and then you pick a model and you fit your data into the model and then you use the model to make further predictions, right? So that is a pretty straightforward idea. And this is the core for machine learning, actually. But you may ask, like we're engineers, we're mechanical or manufacturing or material engineers. Is there any chance that we consider physics, right? Is there any chance to consider physics? Or how? Well, ideally, we want to apply physics instead of just a curve fitting, right? So you may argue with me if you have a model or if you have a testing data, and which one do you trust more, right? I'm not sure. Like different people may have different ideas, but I would say none of them are fully trustable. Why? Because in your data you have your measurement noise, right? You have your limitation from your sensors. But for a model or a physics, you have a lot of modeling assumptions or like a linear assumptions or elastic assumptions, right? So that makes your physics-based model not fully trustable either. So the good idea here is there any way that we can combine these two information, right? Or two parts together. Actually, the math part for this one is called particle filter. So the particle filter is dealing with a state transition model and another measurement model, right? So when your measurement is higher quality, so the algorithm trusts your measurement more, and when your physics is strong, the first principle, and then you trust your state transition more. And I'm just going to skip the math here, but let's think about the big picture here, right? So you have three things you can leverage while you're making any predictions or assessments or estimations. You learn something from your teacher, physics, right? You learn from your stress analysis or other courses. That's physics-based model. And sometimes if you do measurement or you do testing, you have your signal acquired from the test event, right? So you have measurements, which is the second one. And the bottom one is called LSTM network. So that's a machine learning model. So my point here is this is normally what we do, right? For the particle filter idea I just introduced to you. You have your physics, you have your observation, and how to combine your physics with the observation. If the observation is stronger, you trust your observation more. If your physics is stronger, you trust your physics more. But now, my point is, what if you have a physics model that can give you a lot of predictions, but your measurement is only available between time T1 and T2? You don't have measurement forever, right? You only have measurement for a certain chunk of a time period. So in that case, what can you do? Can you leverage something when there is no measurement to enhance your physics-based model, right? So the idea is, yes, this is the conventional machine learning approach. Like we have measurement and we have a machine learning model, and then we train the model, right? So that's the machine learning. So the idea here is that can we just combine the three of those? So when there is measurement, I'm combining my physics-based model and my measurements. And when there is no measurements, I have a pre-trained machine learning model, and I use that machine learning model as the virtual measurements, as the simulated or synthetic measurements to combine it with my physics-based model. And here is an example of how we did or how we implemented. So the physics, where's the physics? We know there's something called Paris law, right? To predict the crack of a system or of any type of material, right? And then we have a state transition model. So that's just a hypothetical. This is our, where's my cursor? This is our measurement, right? So we have two things that we want to combine. And if we only apply the machine learning, so we have the data and we have a model structure and we train the model, right? And then you see like the two curves. The red curve is the machine learning result, and the green is, the blue is the true value, right? You see like they just generate following each other, but there is like an offset. There's some error there. So this is machine learning, right? Or we apply the traditional particle filter, right? We have a physics, Paris law, and we have observation, and then we'll put them together. Well, part of the particle filter, I should say the advantage of a particle filter is it does give you the an uncertainty bound for your estimation, right? So you merge these two pieces of information together, and then there will be a error bar associated with that. So I'm putting like a 90% of a confidence interval here, right? So you'll be able to see they follow with each other, okay, right? Well, the black is the measurement. The black here is the measurement, and this is the median. The black dashed line is the median. It's the prediction, right? And the red is your true value, right? They follow, but they're not quite exactly following each other. And especially there is some parameter estimation that you will be able to see like the true value is actually, the estimation, both the 90% of error bar falls like really off the true value. So that means like it's kind of a fail, right? It does the job, but not a decent job. If we combine the three things together, somehow my okay, so if we combine three things together, and we see like all of the curves clustered to a very narrow band, right? So this is actually the benefit of applying machine learning and the physics and combine them together and to have a much better prediction, right? So are there any questions so far? Or you guys have already lost? All right, so so this is the first part I just show you guys, like how we do a machine learning and how we combine physics on top of the curve fitting idea, right? And the second part I'm going to introduce to you is some of my early work regarding the non-contact sensing, computer vision or video-based sensing, and a particular technology called phase-based motion magnification, and how we use this to identify the system dynamics, predicting system damages, and in the context of a digital twin. All right. So I'm just showing here some of the figures that my colleagues have done before. So there are limitations on the conventional dynamic testings, right? So I'm not sure like how many of you are familiar with the structural testing, but I'm pretty sure you know, like if you want to take data, you have to have sensors, right? You have to have sensors. But if you want more better resolution of your sensor placement, you have to put a lot of more sensors. That if you want a full picture of the system, you have to have a lot of sensors, right? So that means you have a lot of cord, you have a lot of wires, you have a lot of sensors, which may potentially mass loading your structure. For instance, the parachute, right? The parachute is very lightweight, and you can't just like a no-brainer apply the more sensors on top of it. So in that case, we have to leverage something non-contact, right? So do you guys see the animation okay? Is it playing?
Yes.
Okay, all right. So there are some successful non-contact results that me and my colleagues have accomplished. For instance, if you apply optical sensing using video cameras, you are able to figure out the motion of an object, right? You may apply a microphone array, right? These are all non-contact, and you get the full picture, the full field, right? Some more work from my colleagues, right? So you may put the cameras on the drone and fly over a bridge deck or a pier or something. You'll be able to see the crack, the stress concentration, right? So this motivates the optical flow algorithm to do a system identification. And particularly, I want to show you something called phase-based motion magnification. Let me just skip the math here. But this one is a high-level picture. So if you have a video measurement, the algorithm or this technique will give you, will extract the motion from your video information, right? So this is the take-home message, everything that you need to know. Actually, why it's called phase-based? Because your motion is contained in the phase. So the phase of your images or of your videos is actually proportional to your motion. So once you have your motion, you can do a bandpass filtering to filter out the unwanted motion that you dislike, right? And leave only the motion or the frequency component of the motion that you want to see, right? You may magnify that, and then you may do the inverse transformation, and then you may generate some motion magnified videos. So it sounds like a really crazy, but let me just show you an example. You know what I mean. So if you have a beam, cantilever beam, and you just knock it, what you see vibration, right? And the beam just going back and forth, and you see the vibration is actually pretty complicated. It's not like a simple arc, right? But after you do the phase-based motion magnification, you actually decompose the motion into 4 or maybe more different patterns, right? You see like the first banding, the second banding, you see like the higher, like a third and fourth, the higher the pattern is, the more wiggling it is, right? And you see there is somewhere like it's fixed, like this location. It does not move, right? It's a vibrational node. So the outcome from this phase-based motion magnification is actually decomposing the vibration into different orthogonal modes, right? It's like an eigenvalue decomposition. And at the same time, we can magnify that, make it more visible, right? So we apply that onto wind turbine blade. You see there's a wind turbine blade here. It's a full scale, it's actually, right? It's a real, it's not a model, it's a real turbine blade. It's over 2 meters long. And we knock it near the root, like what we did. So if you don't pay attention, you may think this is a figure, but actually this is a video because you see like the hammer here, right? But you don't see actually a lot of motion. Most of the motion is not visible. And after running that phase-based motion decomposition and magnification, so we see clearly the swaying back and forth, right? The first, the second, and the third and fourth modes. And you see the nodal points as well. So if you really want a quantitative analysis, you can figure out where the node is, right? Or you can figure out the extreme, the upper and lower extreme. So you have the vector of the motion. And if you're talking about damage, so we actually did some artificial damage here. So we attached some extra pieces of mass and hit it and then decompose that. So you see like similarly 4 different modes. Well, you can extract the 5 and 6 and higher, but we just didn't do it here. You see maybe you can figure out that the vibrational pattern is different from the previous case before the damage, right? But then we just compare the before and the after damage on the same scale, right? So the red circle and the green dots are actually the baseline, the undamaged baseline and the damaged case, right? So you can see like this is the first, second, and third and fourth modes. So the first and the third modes, they are actually pretty similar. So you don't see actually a lot of changes before and after the damage. But the second and the fourth on the right-hand side, actually very different from each other, right? So we plot the results quantitatively on the right. So we have the bar chart. We have a different. So this is called the lower one is called a modal assurance criteria. So that is actually the cosine value between two different vectors, which is the motion vector here in this slide, right? So you will be able to see like the first and third mode are actually pretty close to 1. So that means they are very orthogonal. So because it's supposed to be orthogonal, right? And after the damage, right? So you see like a loss of your MAC value. So that means like they're getting different from each other. So I mean the second and the fourth mode before and after the damage. So they're getting dissimilar to each other, right? So the top right figure. So that is actually a frequency comparer, right? Comparing the frequency extracted for the first 5 modes using different approaches. So you may just figure out, so wait, we just have 4 modes, right? But why we compare 5? The reason is we have only mode number 1, 2, 4, and 5. Why there's no number 3? The number 3 can be extracted from accelerometer data. But from the camera data, we can't extract the mode number 3. Why is that? Because this mode is out of plane. So you can't see things moving in and out of plane, right? With a single camera or with your single eye. You can't see things, you can't see the depth. So now, is there any capabilities that we see the depth? Well, 2 eyes, right? Open both of your eyes. So similarly, using the computer vision approach, you just apply 2 cameras. You synchronize the 2 cameras. And then there's an algorithm called digital image correlation. So you can correlate your 2 cameras, or another way, your 2 eyes, right? And then the idea here is, can we motion magnify the videos from the 2 cameras and keep them still synchronized and see if we can get something more valuable out of the plane, right? Or more visible out of the plane. So the same wind turbine blade, and we run a finite element model for how many modes? 1, 2, 3, 4, 5, 6, 7 modes. And 7 modes were extracted from the operational model analysis or structural testing, right? And we compare that with a finite element model. And those are associated with all of the peaks. 1, 2, 3, 4, 5, 6, 7 peaks in the power density function. I'm not sure if you are familiar with the power spectral density or power spectrum density function. It's actually a transfer function idea. If you have a peak here, that means you have a resonance. You have a natural frequency near this frequency. But you have 7 modes extracted, but are there higher modes available? Well, from your finite element model, you of course you can have mode 8, 9, and 10, right? You have higher modes. But for testing, because of the signal to noise ratio is so poor, you don't see that, right? So you see peaks here, but do you see peak here? Do you see peak here? Or are these spikes the real peak? Or is this a peak? Is this a peak? Are they like a resonances, or are they just a noise? You don't know, right? And I'm putting 2 red arrows here. So these are actually the prediction from my finite element model. So the finite element model tells me there is a mode here. It's neither this peak nor this peak. We're probably very close to this peak. And this one, there's no peak at all, right? So what's going on? Let's just run that motion magnification and take a look at it. So this is the result, right? Before I run any motion magnification. So I have a mode 1 to 7 extracted, but mode 7 is actually pretty poorly extracted. So the MAC value or the consistency value is only 84%. And mode number 8 and 9 are failed. So you don't see that in your data. You don't see these higher frequency components. And then after the magnification, this is a mode number 7, right? So the peak used to be here. And then we can bump up this peak from here to here. It's more than 20 dB. So that's a pretty big improvement. So make something like just a barely visible to make it very obvious. And that model assurance criteria value bumped up from 84% to almost 90%, right? So that's mode number 7. And mode 8 and 9, we didn't extract them at all, right? And this region is a suspicious region, and we know there might be a peak, right? And then we figured out after the magnification, this peak got bumped up. It's actually somewhere here. And this spike was pure noise. And this spike was actually here, this one. And this spike is here, right? So these are actually fake peaks, like here, right? So this algorithm is pretty much noise robust, right? So the noisy peaks do not get amplified, but the real motion got amplified. So that's mode number 8. And mode number 9 is the same story. So we didn't see like a very informative stuff here, but after the magnification, you see a very clear peak. So that's mode number 9. And quantitatively speaking, so we have like all of the modes are over 80% in terms of the MAC, right? So let's just wrap it up a little bit. Why this is valuable for digital twin? Because at the beginning of today, I said like a digital twin is a online monitored and online updated model, right? So that means if your system has anything changed or the system has anything that is invisible, it's not going to be, or it has to be reflected in your model. So being aware of these changes or being aware of these non-extracted higher modes are critical to the digital twin, right? And another thing is that higher modes are actually more likely to be affected by damages because the damages most likely are local, and the local changes of your system parameters will affect the higher modes first before they affect the global lower modes, right? So this is the benefit, right? If you are doing damage detection, the higher modes are really critical because they are the first to be affected by the local damages. And something like we can leverage using this algorithm is the cross-section validation. Because while you're designing a turbine blade, the cross-section of the turbine blade, you may want to do some wind tunnel testing, or you may do some other design verification, right? So, so this will give you some leverage. So you have there's how many? 5 different modes that we extracted, right? So you have this like a rocking mode, right? Rocking back and forth, and this is the breathing mode. So you have different modes associated with different frequencies. Or you may made it like a full scale, right? This is the wind turbine testing center in the Massachusetts Clean Energy Center. We actually collected some data and run this, the same idea, the motion magnification, right? So you'll be able to see more visible the motion, and you see where the node is. And for out of plane, this is something done by my colleague. This is the out of plane using 2 cameras, right? So you'll be able to see the in and out of plane motion. you may also apply this to to the field test, right? So this is a commercialized like a toolbox from RDI technology, and you can see like the motion of the tip of a wind turbine or the nose of a wind turbine is actually extracted in real time, right? So all of these are pretty useful and critical to the big idea of digital twin. And before I finish my presentation today, I wanted just to share with you with some of my students' projects regarding the non-contact sensing, image processing, video processing, that sort of things. This is a really some serious application. We got this project from Redstone Arsenal, and they're interested in real time how the operational modes for a missile is because you can't just do a lot of wire testing from the ground, right? Because of the missile is flying, or sometimes you deal with a project that you work on every weekend, right? It's a dryer cabinet, and we apply the digital image correlation to figure out the vibrational modes and the strain distribution, right? So this is very useful for their design and the noise mitigation, right? And it doesn't have to be related with the system dynamics, right? You can use this optical sensing and computer vision to trap a car or to track something other object that is moving, and we can calculate the time that the car get into the red box and getting out of the red box, right? And calculate how much speed the car is. So this is the capstone project I supervised a few years ago. Or it may get bloody, right? So if you because if you have like a fan or a car engine, you would just say, yeah, put a sensor there. But what if you have like a rat leg, right? It's the front leg of a rat. Where are you going to put the sensor on? Well, we have a sensor here, but the mounting for the sensor may not be very secure, right? This is a cow bone, right? Or this is the egg yolk, right? How to put a sensor on the egg yolk? They're hard, right? There are some solutions, but it's very hard. But non-contact sensing is pretty advantageous here. And or it may not be that nerdy. So you can use non-contact sensing to figure out the system dynamics and acoustics characteristics of your music instruments, right? Or something like your neighbor is jealous about you, right? So this is a project my student using they just designed this system to knock the pavement and to figure out if there's a delamination or pothole or early stage of a pothole, right? You'll hear it if that sounds solid or that sound hollow. So you can use a like a sound analysis, or maybe just to use a camera to figure out if there's a pothole, right? Automated detection. All right, so I think I'm right on time. So before I finish my presentation, I want to acknowledge all of my students. I'm the cheer lead, and they're really the workhorse. So some of them are graduated, some of them are not. And also, I have to acknowledge all the funding agencies who provide the financial support, right, to finish all of these projects. And if any of you are interested on the like a structural health monitoring, signal processing, machine learning, or you have a question, so you want to discuss with me in further details, you can just reach out to me. And my office is in Washburn 234. So with that, I would like to thank you for coming and answer any questions.
Thank you very much. It was a great presentation.
Thank you.
So I think we'll give a few minutes for anyone to raise hand or unmute themselves for asking questions. Yes, Professor Brown.
Hi, thanks. Very interesting presentation. That was neat to see all the stuff you were doing.
Thank you.
For measuring, have you considered reflectance technology? So rather than using two cameras to do binocular sort of vision, get the you might use multiple cameras or just CCD arrays and get the spectral reflectance direction, and then be able to reconstruct the geometry from that. The problem that I've had using two different viewpoints like that, trying to put it to get photogrammetry type, is that you only get a height difference where you get a pixel shift for the same feature. And if you get 8 pixel shifts, it's a lot.
Yeah.
So then you only have 8 different heights. So your height resolution is poor.
Right.
So you could do some sort of polynomial texture mapping, and that technology has already been worked out. And then and be able to figure out, have much better height resolution.
Yeah. So the DIC leverages the interpolation, right? The polynomial interpolation.
Yeah, but it's you're not interpolating between just 8 points, and the interpolation is much different. You're not interpolating height positions, but you're interpolating normals.
Well, yeah. So I mean, I think my general comment for your for a question is there are different algorithms. Some are like a subpixel, like in the motion map, the phase-based approach, that is a subpixel. It may get us a little bit better resolution without like leveraging the interpolation.
Yeah, I have read, not recently, but some years ago, the subpixel resolution stuff, and I didn't see where they were really getting that. They were just doing interpolation, and there is no evidence that it should be a particular interpolation, if it's linear or even a polynomial, particularly when we're looking at actual surfaces. But anyway, I'd love to talk with you more about that.
Sure.
The other thing that
talk about that, yeah,
came to mind, if I still have a minute, you can shut me up if somebody else is.
No, you have your time.
The vibration on the wind turbine blades, I thought was fascinating. Back in the late 70s, when the PDP-11 came out, that was a computer for those of you who weren't around back in the late 70s. It was a great lab computer, and it could do Fourier transforms, and it could figure out vibration modes. And Rossignol, a French company, hooked up with University of Grenoble in France in the Alps, and studied skis, very similar problem. And it turns out that you've got good vibes and bad vibes in the skis. And so then they did selective damping to damp out the bad vibes.
Yeah.
And their skis cleaned up in the next World Championships at Schladming. And so I'm wondering if the same sort of technology might work on the blades, because you put in damping material at the high energy locations on the bad vibes, so you damp those out selectively.
Oh yeah, yeah, definitely. Dampings were made probably like adding more viscous material in the area, as what you said, like a bad vibes area, right? I'm pretty sure like those wind turbine blade manufacturers, they did a lot of like effort on this. We're trying to like reduce the. I know like in the sports engineering domain, like a skis or even like a golf pole or something people spend a lot of effort on that to improve the dynamic characteristics.
Yeah. Well, that's a good place to try it out, because the consequences of it not working well are, if it's a golf club, are much less severe than if your turbine starts coming apart.
Yeah,
those are big and high up and expensive to fix.
Exactly. Yeah.
Well, that's pretty neat. I hadn't seen that before, so thank you for showing it to us.
Thank you. Yeah. Well, thank you for a question.
Okay, I think we have time for one more question.
So which digital twin won?
It was Wally won by quite a bit, actually.
Oh, that's because everybody thought he's the provost.
Maybe right. Great. So Zhu, I should have let you know that we do these attendance polls to just see which have a record of grad students that are here. So great. Okay. Yes, Moana came in last with just 5 votes, and Pikachu and Optimus Prime are about even. Wally was way ahead with 19. Great. Okay.
All right.
Well, if there are no other questions, we can wrap up here so people can get to 1 o'clock classes and meetings. So thank you very much. I really appreciate it. Very interesting seminar.
Thank you. Thanks for inviting me.
Thank you.
Right, it was a neat capability to see how you can get some of those higher modes. So very interesting.
All right. Thank you. I will. Yeah, we can talk in more details.
Terrific. All right.
All right. Then I will talk to you guys later.
Okay. Right. Bye-bye. Bye, everyone.
Bye, Chris. Oh, Chris is left.